Before we get started, I want to do a little thought problem. I have here 2 coins. I am going to flip them. Alright, I'm going to look at them, and I'm going to tell you one is ahead. Now, what is the probability that the other one is ahead? Think about it for a second. Okay, if you said that the probability that the other is ahead, I'm afraid you're not quite right. Or the probability is 50-50 that the other is ahead. You're not quite right. There are 4 possible conditions when I flip 2 coins. I can have 2 heads, I can have a head and a tail, I can have a tail and a head, or I could have 2 tails. Well, we know it's not 2 tails because I told you one of them was a head. Now, that leaves 2 heads, a tail and a head, or a tail, a head and a tail. So there's only one of those 3 remaining conditions that is possible now, and that's 2 heads. But there's 2 situations where there can be 1 head, 1 tail, 1 tail, 1 head. And so the probability of the second being ahead, or the other coin being ahead, is 1/3. Now, if I had done my little study a little differently, and I flipped a coin and I told you it was a head, then I went to flip the other coin, the probability that I got a second head would in fact be 1/2, 50-50. So those are independent. Now, those events are independent. We multiply the probabilities, 0.5 for the first one, times 0.5 times the second, and we get the probability of a head at being, or the probability of having 2 heads is 0.25. 0.5 times 0.5 is 0.25. Probability of 2 heads. Over both flips, we're going to use this information in order to diagnose glaucoma. So glaucoma is a disease that develops slowly, and you don't really have any symptoms that you can tell at first, and after a while it's finally ultimately diagnosed when you can look at the eye and see that the nerve fibers going through the optic disc are deteriorating. But for a long time they can do that and you don't really notice it, and as an optometrist you can't see it. So there are a number of measures we use to screen for glaucoma, and these will be a little abnormal before a person develops glaucoma. Now, the ones that are usually thought about, or some of the common ones, are the age of the person. The older you are, the more likely you're to have glaucoma. Intraocular pressure, that's IOP, pressure inside the eye, and that's basically the way, if you see a patient, you think they're developing glaucoma, or even if they have glaucoma, the way you treat it is by giving drops that reduce this pressure. Those drops tend to be a little expensive, and you have to take them forever, and they're not comfortable, and oftentimes you take them more than once a day. Another measure is central corneal thickness. So the thicker your cornea, the less likely you are to have glaucoma. The vertical cup to disc ratio, that's a measure that actually you will be doing, and it's when you go in, you either take a picture of the optic disc or you go in and you directly measure it through BIO. The Humphrey Visual Fields Pattern Standard Deviation. Now this video is an example of how you use standard deviations, or how standard deviations are important in various aspects. Well, actually they're not even just important for describing the spread of a distribution, but sometimes they're actually used as an outcome measure, as in the Humphrey Visual Field Pattern. So the more variable the output is from this instrument, the more likely you are to have glaucoma, and they measure the the mean of a parameter and look at the difference of each observation and see how a person does. And if you're more variable, you have a higher standard deviation, and that's problematic. So I put together this spreadsheet to kind of talk about things. And our little flipping the coin example was designed to illustrate how this works. So any one of these measures can have a probability that we can look at the probability of what each of these is in normal. Now there's not really a normal age, you just kind of go through it. But for IOP, if you don't have glaucoma, there's kind of a mean for that, and we talked about that earlier, and a standard deviation. The mean, in fact, is in this example, this data set is 17.6 with a standard deviation of 2.2. If you have glaucoma, the average glaucoma patient has a mean of 24.9 and a standard deviation of 5. Now, we can go through and we can look at all of these corneal thickness and vertical cup to disc ratio, 0.35 to 0.43. Humphrey, standard deviation, 1.94, 2.01. Now, let's look, and basically what we're going to do is, to give you kind of an overview, we're going to look at the probability. If you're normal, what's the probability of getting a particular number? So here's an example. We're going to have a sample, and in this sample, or this patient rather, the patient is 60 years old, their IOP is 20, their central corneal thickness is 490, their vertical cup to disc ratio is 0.35, and their Humphrey visual field is 1.94. So for these last two, 35 is the mean for that, and 194 is the mean for the normals there. Then what we're going to do is we're going to calculate the probability that you would get these numbers, if each of these numbers, if you were normal, or I should say non-glaucotomous, not necessarily normal. And what is the probability if you had glaucoma? So here we have, these are the probabilities if you're normal. These are the probabilities if you have glaucoma. And actually this probability in this case is called a likelihood. And we'll get into that a little bit more. But basically what we're going to do is we're going to multiply these probabilities, just like in our coin situation. If we flipped a coin 5 times, what is the probability that you would of finding so many heads? And that's how this works. Now we're going to do this. We're going to come up with a number, and we're going to see which one, after we've multiplied in both of these cases, which one is more likely. Are you more likely to get this set of numbers if you're normal or non-glaucotomous, or if you have glaucoma? All right, and on the way there, what we're going to do is, in analyzing this, is we're going to calculate Z-scores. Now, we talked about Z-scores earlier. And a Z, remember, is the value 60 minus the mean, 56, divided by the standard deviation, 9.9, equals 0.394. Now, I have gone out, and that 394 is in units of standard deviation. So that's called a Z-score. Sometimes it's called a standard score. So if we come down, this graph here I've laid out. Here's our Z-score formula. And we get a score of 0.39. So that's going to be around here someplace. So if we come up, we're going to see that this value falls around here and is somewhere around here. In fact, given that we know this is a normal distribution, if we have this standard deviation, we can look up in a table and find that the probability for the 0.39, for the being 60, is the probability, the point on this line across here is 0.369. We do the same thing with the IOP. We have 20 minus 17.6 divided by 2.2 gives us a z of 1.091. So the z here gives us the probability, I guess we're going this way, given that you have 0.25, the z is 1.091, so that's right down here, it's about 1, and the probability is around 0.25, so 1.09 probability, the exact probability on the normal distribution is 0.220. A normal distribution is a mathematical distribution. It looks like this right here, and so there's the standard deviation, there is the mean, there is the standard deviation. That's basically a z-score embedded in this thing. And so we find that our z-score is 1 point. We come up the probability, or this case, it is 0.2. We do that for each of them. The central corneal thickness, the actual patient's value is 490 minus 577 divided by 36 is minus 2.41. So that's out here. And the probability of being normal, and if you're normal, the probability that you would get a minus 2.47 is 0.022. And with vertical cup to disc ratio, it's 35 minus 35 is 0, divided by 0.2 is 0. The z-score is 0, so you're right at the middle. And interestingly enough, being at the middle doesn't mean you're at 50%, you're at 40%, 0.4, 0.399. Okay, and that's the same way with both. Notice these two measures the Humphrey visual fields pattern standard deviation. The mean's 194, and the mean of this one is 0.35, but they're both right on the money for being normal, so they're both a z of 0. So the z-score kind of standardizes everybody and puts them in the same context. So all these numbers are different, all these samples and the scales are all different, but we've standardized them into normal scores and put them on a distribution here that lets us figure out the probability at this particular point. Now, I've called this a likelihood, and I don't call it a probability. And so just to have a definitional distinction, when we're 0, the likelihood of finding a 0 is 0.4. The probability of finding a 0 is 50%, because we consider the probability, the word probability has a cumulative sense to it. So it's all the values to one side or the other of this curve. So probability talks about cumulative information, while likelihood is a single point on this line. When we talk about p-values, we're going to talk about 0.05, and that's the probability of finding a value of 2 or greater is 5% if we do a one tail, or it's it's 0.25 here, and then you add up another 0.025 here. So the total of plus or minus 2, even though we get a number that's out here where we add the tails in, it's a little confusing, but the probability that we would find a number so extreme as a number greater than 2 or less than minus 2, that's a two-tailed test, as opposed to a one-tailed test. A two-tailed test is 5%. So, and it's that because it's cumulative. We don't use the single probability point when we get it. We use a cumulative number. But in this likelihood thing, we're using a single point and calculating a probability. One other thing that we do when we're multiplying these little numbers, we get into tiny numbers. Tiny numbers, the computer doesn't like that, and they run into a condition called underflow, and it can't calculate it. The resolution isn't good. So what we do is we take the log of this number. So the log of 0.369 is minus 3.289. So we take the log of all these numbers, and then when you take the log, instead of multiplying like you would multiply the probabilities there, we add them all up. Now, this process is called Gaussian naive Bayes. And it's Gaussian because we're using a simplified model of the normal distribution. It's naive because we treat them all the same. We don't say that one's more important than the other, and that it also is using this single distribution. But it's Bayes because we incorporate what we already know. And what we already know, or what we can find out in any event before we do, is the prevalence, and that's called the prior probability. And in the case of glaucoma, or a case of your patient, when a patient is in your chair, you know that in your particular practice, a certain number of your patients are going to have glaucoma. You don't know what's what, but you know based on your practice, your demographic, and in this case, we've said 2% of the population, 2% of your patients have glaucoma. So before you take any tests at all, a person sitting in your chair, you say that person has a 2% probability of having glaucoma. And then what we do is we add the probabilities of all these other measures to this prevalence. So Bayes, the difference between Bayes and just other kinds of statistics, just multiply those and leave it with whatever probability you get. So for example, you just measure IOP and you say, well, the probability of my patient having glaucoma is 22. So we add, or we multiply this 0.02 if we're doing the normal likelihood. We add the log of it, which is minus 0.02, or minus 3.912, with 2%. So there's a 98% probability that they don't have glaucoma, and that's a minus 0.02 log that we add. Now we have these log likelihoods of all given these data, we have the overall likelihood, the sum of all these log likelihoods is minus 12 to be normal or non-glauconomous, and it's minus 10 to have glaucoma. And so in this case, 10 is actually the bigger number because it's less negative. And so a person has I did this wrong. Let me go this way. I'm sorry. we're going to take this number and we're going to divide it by this number, and we're going to get a likelihood ratio. So this person has a 0.849, and sometimes it's easier to that's why I did it the other way, to take the inverse. So a person in this case is basically 17%, or 84% less likely to be glaucoma, or more like 0.849 less likely to be normal, 17% more likely to be glaucoma, have glaucoma. So bottom line here is this number for normal is a smaller number than this. So you're closer to the probability of having glaucoma if your patient has these values. All right. Another thing I wanted to show you was, well, there's a couple of things. But first, this curve right here, these curves, are the means and standard deviations of people that are non-glaucotomous and have glaucoma based on their age. So we have here, the person is 60 years old, and so this line shows you where that is. So there are, this is 60-year-olds. You can see that the glaucoma curve is shifted a little to the right. But also, if these are all your patients, you can see that, there is a lot of overlap here. And so you have to be careful when you think about the numbers that we're talking about and when you're doing diagnosis. And let's just give the example of IOP, which is right here. Here's the shift. Now remember, I mentioned earlier that in a previous video that this is doing them this way is what the graphs would look like if 50% of your patients were glaucoma and 50% were not. The height of this curve, if you did the overall probability and shared it between the two, the height would be much different. The red would be down here. But you can see there's a shift in to the right, higher IOP, and that's why people look at IOP, because it's just, there's this shift going over here. But there's a lot of people who are normal or who have glaucoma that have values down here, just to kind of show you how this works. And let's make their IOP 15. Now you're over here. And if we look to see what that did to our not sure it changed it. It did. It made them more, well, they're still glaucotomous. I think part of the problem was this guy. The corneal thickness was really thin. And so that made them, given their age, a lot more likely to be there, have glaucoma. It just shows you these measures can bounce around. You can have a person with a lot of things. If you were trying to just look at those numbers and determine whether that person has glaucoma or not, it would be very difficult. But once you start piling on with these different tests and you have this mathematical way of combining them, then you can see where they are. But I think what I wanted to do was also show you effect sizes. So when we were talking about age, if you are normal, your age is 56, glaucoma 59, the effect size is 59.3 minus 56.1 divided by the average standard deviation of 9.9 and 9.5, which is about 9.7. So this difference divided by the average standard deviation gives you an effect size of 0.33. So that's less than our clinically relevant standard. The effect size for IOP is really big. This one, even though there is all this overlap, that's still a 2 standard deviation difference between the mean of this distribution and the mean of this distribution. Again, effect size calculated by 24.9 minus 17.6 divided by the average of 2.2 and 5. And that difference divided by the average standard deviation is 2.028. Now that's just the difference between the means. This is the kind of like the overall impact of a particular test. You could probably, well, there's different weight. In our naive, we treat all these differences the same, but they could have slightly different weight. But I want you to understand, we're looking at observations. There's just normal variation. This is just normal variation for people that have glaucoma and normal variation for people who don't. And sometimes you can have glaucoma but be perfectly normal. All of these people right here in the red line have an absolutely normal IOP. There aren't too many people that are not glaucomatous that have a normal or have a usual IOP for glaucoma. So we're looking at the difference, but here we can see this massive overlap in things, and so you're taking little bits, little pieces of differences, and you're adding them up, and you're looking to see, are they closer to normal or closer to glaucoma, and then the winner is the one where you're leaning. Now, if you were as close as 12 and 11, you probably wouldn't change your practice too much. So what is commonly said in you'll get in your classes is you get somebody that has maybe a high IOP at 23, 24, 25, something like that, maybe even higher. You're going to say, we're going to follow them. Well, when you follow them over time, what are you looking for? And what this particular tool does, this Gaussian naive Bayes formula, allows you to follow them a little bit more closely and maybe start them on drops a little sooner if these numbers, these two sums, differ by a lot. Okay, I hope that this example has shown you some things that you need to know. How to calculate a Z-score. The Z-score for normal people is the value 60 minus the mean 56 divided by the standard deviation. The Z-score for glaucoma is 59.3, the mean for glaucoma, minus, or the sample 60 minus 59.3 divided by 9.5 gives you a Z-score of 0.074. And the smaller this, the closer this number is to 0, the closer you are to having glaucoma. The closer this number is to 0, the closer you are to being normal. And then we figure out that closeness by calculating the likelihood, taking the log of the likelihood, adding it up, and then adding the information about the prior probability, the prior chance that somebody who's sitting in your chair, the probability that they're going to have glaucoma before you do any tests. You add them all up and you get your answer. All right, that's your example.